Okay, so it's just gone past. Good morning. Thanks for the introduction. I am Ian Shemilt, but really I've prepared this talk with lots of help from Professor James Thomas, who I'm standing in for, so he deserves at least half of any credit, but of course any of the blame is all mine. Here's James, not only my friend, work husband and boss, but also I imagine even in my less neurodivergent moments, a beneficent Time Lord who's travelled back from the future to tell us what's going to happen there and gently nudge us in the right direction. We both work at the Epicentre at UCL, where we develop methods and tools for systematic reviews and other evidence syntheses, leveraged by the reviews that we do to inform decision-making in various fields of public policy and practice, including lots on health and public health topics. And where his and my research interests coalesce most around developing automation tools for making these processes more efficient. We also have our in-house software, Epi Reviewer, which hosts the automation tools we develop and make available for others to use. So I'm going to begin with some context, evidence synthesis for decision making, then I'll say a bit about current standard practice, and then the main part of the talk will focus on how machine learning is and might in future help us with this work. An important theme will be that in most evidence synthesis use scenarios, the benchmark levels of human performance that we're aiming to attain with automation are really quite challenging. That is, our objective is invariably to maintain the high accuracy of current practice, whilst also reducing the amount of effort involved. So what is evidence synthesis? Well, broadly, it's research that involves combining information from multiple studies on the same topic to comprehensively understand their findings. The idea is that all other things being equal, relying on cumulative evidence from multiple studies can provide more reliable information than relying on single studies alone. It can be used to help determine how effective a particular intervention is or how people experience a particular phenomenon, intervention or service. And the ultimate aim is for policymakers, professionals, researchers and the public to use the findings to make better decisions. The term evidence synthesis encompasses a diverse family of methods, and I'm going to introduce just two prominent members of the family now. So systematic reviews are undoubtedly the best known form of evidence synthesis. Conducting a systematic review is necessarily a team sport. It involves methods and topic experts, ideally working together to identify, appraise and synthesize data extracted from all research studies that meet some pre-specified eligibility criteria to answer a specific research question. And the emphasis on all here highlights the often justified levels of aversion to losing eligible studies typically adopted for systematic reviews and the high bar this sets for our study identification tools. Review teams use explicit, predefined methods aimed at minimising bias with the aim of producing more reliable findings. For example, we usually use at least two people independently, duplicating the same key tasks and then discussing and resolving discrepancies. And the process has several stages, which are shown here, which collectively operationalise the identification, appraisal, synthesis and interpretation of relevant evidence. There are various kinds or flavours of systematic review, and this examples a recent Cochrane Public Health systematic review assessing the effectiveness of interventions to promote use of seat belts. Another methods framework in the evidence synthesis family that's gained popularity during recent years is the evidence and gap map, or EGM for short. Compared with a systematic review, developing an EGM likewise involves finding and selecting research that meets pre-specified eligibility criteria and the use of explicit systematic methods. However, the expectation that a reasonable attempt is made to identify every single last eligible study is slightly relaxed for an EGM, albeit in practice not by much, due to the different purpose of mapping, which is to provide a descriptive overview of the overall landscape of research evidence in a typically much broad area of research in the systematic review, including any gaps. Producing an evidence and gap map occasionally, as in the example we'll see in a moment, but often does not entail appraising included study quality, nor does it usually involve an aggregating synthesis, such as a meta-analysis of the results of included studies, although these maps and their gaps can and do usefully inform questions for new systematic reviews, as well as for new primary research studies that are designed to fill the gaps. In this example, noting that the image doesn't show the entire map, studies identified and described in the EGM of interventions for reducing violence against children have been visualised here with types of interventions assessed on the x-axis, types of outcomes measured on the y-axis, and the segments, the circles in each cell, which in this case delineate two levels of study quality, first for impact evaluation studies, the red and yellow circles, and second for systematic reviews in green and blue. However, it's doing evidence synthesis properly that's also led us to using inefficient, time and resource-intensive manual processes that produce very reliable but expensive and time-consuming reviews. And this is coupled with the perennial struggle we face trying and sometimes failing to keep pace with data deluge. For example, for Cochrane reviews published back in March 2014, the last time we counted these up, 163 citations were screened, 6,500 full-text reports were retrieved and read, and 703 studies were included, and that's in just 1 month's worth of reviews. At that rate, around 2 million records were screened by Cochrane authors during 2014, and in duplicate too, because doing so individually is just too inaccurate. And extracting the data, again in duplicate for results data from 703 included studies, would have taken many months' worth of manual effort. And of course, that's 10 years ago, and the sheer quantity of research has increased quite a bit since then. So all that sets the scene for why we need to automate evidence synthesis. Conventional standard practice manual evidence synthesis processes, while very accurate, are also very time-consuming and costly. Producing reviews and maps takes too long, and this means related decisions are sometimes made before we can actually produce the synthesized evidence and bring it to bear. Findings can also quickly become out of date, sometimes even by the time we publish them, and so what we need is more efficient ways of doing the legwork. But that doesn't, in my view, mean that we need more so-called rapid reviews, in which corners, that is, rigorous processes designed to assure quality and reliability to minimise bias, are essentially cut. Rather, what we want to be able to do is produce high-quality, accurate evidence synthesis with more or less the same rigour we have already established with conventional manual processes, recognising that there will always be a trade-off with automation, just getting the job done much faster though. So now on to the main part of my talk, which is a whistle-stop tour of 5 ways in which machine learning is enhancing or might one day enhance evidence synthesis production. Automatically clustering and visualising search results, classifying studies, screening studies for eligibility, finding new studies for living reviews, and information and data extraction. So first, coming from the unsupervised area of machine learning, there are lots of tools that will automatically cluster studies into thematic or topic groups based on the text features they contain. And you can get some nice visualizations of the relationships between concepts and of clusters of documents, and you can see roughly how many records there are in each area and so on. And that's to help you explore and understand what's in your search results. And these unsupervised approaches are very powerful in that they can usefully reveal relationships and important clusters in the topics in the data, which is quite handy when you're thinking about getting an early handle on what you've retrieved or what coding scheme might need to look like for when you're mapping research, for example. And these approaches are also low cost because we don't really have to do much. We just upload the data and then the tools manage the rest of the process for us. However, the critical weakness is that they lack control. That is, we can't specify in advance how the records get clustered, which moves us nicely on from unsupervised to supervised approaches. And this is an example of using a machine learning to classify types of study. And here we do get to specify the classes. So we had a bibliographic records from Cochrane Crowd, which is a crowdsourcing platform where thousands of contributors collectively looked at hundreds of thousands of records and classified them according to whether or not they report a randomised controlled trial, or RCT. This data set is high quality because it's underpinned by a robust agreement algorithm, and the classifier has been calibrated to achieve 0.99 recall, so it identifies 99% of RCTs. And again, that speaks volumes to how accurate the community is looking for these tools to be. But while recall is high, precision is quite low because of the pressing need not to misclassify things. Systematic reviewers would much rather screen thousands of records than they would lose eligible studies. And for that reason, even though it's very accurate, it's being used in live reviews now, this classifier hasn't eliminated all the manual work in distinguishing RCTs from non-RCTs. Furthermore, the weakness with supervised approaches like this is that they're highly dependent on the quality and coverage of the training data. So in this example, we have lots of high-quality training data, and that enables us to build a very accurate classifier. But in other situations, we simply don't have that, in which case the supervised approach is precluded. It's also highly context-dependent. This is an RCT classifier for records of health domain studies retrieved from health databases, and it's unlikely to be much good at identifying RCTs in education or in crime and justice, or in any other topic beyond the health domain where vocabularies differ just enough for the performance to fall to unacceptably low levels. Creating lots of high-quality training data is also very expensive, and therefore when we don't already have it or aren't producing it as a byproduct of what we're doing, we may not have the time and resources to create it either. One situation where we often don't have the training data is when we start a new review. So to get over this, priority screening has been developed, and that involves ranking screening results. If you look at the flow diagram in the bottom right, The workflow is that we enter our search results into a database and then begin by screening a random set of records from the much larger set of search results to give us an unbiased sample of what the overall data set might look like. Then we train a machine learning model based on that relatively small random sample of records, and we apply that model to all of the remaining search results that haven't yet been screened, giving us an initial ranked list of the unscreened records in order of those most likely to be just relevant. And then we start screening records at the top of that list. We might screen the top 25, and then decisions about the eligibility of those 25, plus the records that were screened beforehand, are fed back into the machine learning, a new model's built based on slightly more data, and all the remaining records are then re-ranked and returned to the review to screen the next 25. And so we go on around that loop between stages 3 and 4 until a stopping criterion is reached, or else we've got to the end of the screening list. What we find when we're using these types of approach is that the machine learning is very good at finding records that look very similar to the ones we've already screened and said are relevant. What the challenge is, though, is that we don't necessarily know, when using a system like this, when we've got to the end of the list of relevant records and only have the irrelevant records left to screen. So what we really need to make best use of this kind of tool, and what state-of-the-art R&D for priority screening methods is focused on at the moment, is a validated stopping algorithm. Another area of using machine learning that's becoming increasingly important is keeping up to date with new evidence as it's published, known as continual evidence surveillance for living evidence synthesis, living reviews, living maps, and so on. And the need for living evidence synthesis was particularly highlighted during the COVID-19 pandemic. For example, we were commissioned by the UK Department of Health and Social Care to maintain this living map of research evidence on COVID-19, which today contains around 250,000 records of research articles partitioned by topic. What we developed, tested and then deployed for this living map is a semi-automated continual evidence surveillance workflow that begins with automated searches of OpenAlex, which is the world's biggest open access database of research, with about 250 million records in it. And we grab the tens and sometimes hundreds of thousands of new records that get added to OpenAlex each month. And we've got our living map and other reviews and maps sitting in our EPI Reviewer software. And what we did was to build a machine learning model for the living map and also for all the other reviews and maps in the system that subscribe to the service. And every new record gets scored by this first model that's been trained on known records to learn the scope of this map and all of the other maps in the system. And those records which the model considers closest to the map are automatically imported into EPI Reviewer, same for other reviews and maps. And then for this particular map, a second machine learning model, which is a BERT model, assigns each retained record to one of our broad topic codes for included studies, treatment evaluations, transmission diagnosis and so on, or to an excluded code, not shown here. Or the model can't tell, so doesn't assign a code, also not shown here. And then the records are either automatically included in or excluded from the map. And previously, records that the model was unsure about had been referred for manual screening by a human, assisted by the priority screening tool I talked about earlier. But actually, about a year ago, we took our human screeners out of this loop completely. And what started out at the beginning of 2020 as an almost entirely manual process is now almost entirely automated. It's fair to say that some of the tools I've highlighted so far might be considered a bit old hat these days, but we think they're worth covering in a presentation like this because actually there's been a lot of validation work on their use. And unlike the latest technologies I'm about to mention, they're actually being used in some reviews now, albeit not routinely. However, what people are talking about a lot these days are approaches where supervised and unsupervised machine learning approaches are being used together. The theory is that when humans read, we read in the light of our pre-existing knowledge. And the RCT classifier and priority screening tool that I showed don't do that. So there's been this shift towards trying to inject more context into our ability to use machine learning tools. And we've had word embeddings and we've had transformer models like the BERT model in our COVID-19 map showed just now. Now, of course, it's all about generative models like the GPT family, Llama, Claude and the like. However, it's important to bear in mind that essentially these are all just very sophisticated, very large statistical representations of words and phrases that tend to go together. They're about next word prediction only. And the challenge for us is that whilst this new generation of tools promises to deliver more than the marginal increases in efficiency realised by their predecessors, they're also a little bit unsettling maybe, with the potential to disrupt the science and art of evidence synthesis significantly. But can we use them? Well, what we aren't seeing as yet are many rigorous validation studies of these Gen AI-based tools, spanning lots of reviews and maps with different characteristics. And those are really needed to support the use and development of the tools for evidence synthesis. What we're seeing instead is a smorgasbord of new tools being released and lots of articles getting all very excited about the possibility of using Gen AI for these applications, coupled with an emerging evidence base for performance that's already starting to become massively polluted with limited small-scale evaluation studies of tools being tested in single use cases selected for convenience. In other words, making the rapid the enemy of the good. So the tool development and the excitement are running an awfully long way ahead of the validation studies. In that context, I'm just going to very quickly mention two examples, and these are only illustrative in that context. They're not for publication, certainly not yet at least. First, we've recently been experimenting with using GPT-4 to map the emerging literature on AI inequity, which is another evidence and gap map. We have 26,000 records. We use GPT-4 for screening and selecting records, and also for mapping to assign selected records to some predefined descriptive codes. And this mapping task took a few days for GPT-4 to complete, the GPT-4 even, and costing around €950 in open API fees, and for sure it's less than 100% accurate. The screening phase identified around 9 out of 10 of the correct records, so fully automated screening would have meant losing some eligible studies that were in practice identified using the priority screening tool by humans. So not bad, but also not quite at the level of performance that I'd really like for one of our maps. And the GPT-4 assignment of records to codes wasn't terrible either, but whilst it was rated as fit for purpose by 2 evaluators for producing an initial but not final version of the CGM, the purpose does not require the level of accuracy we would need for systematic reviews. So if this had been a systematic review, it wouldn't really have been rated as fit for purpose. All in all, a lot more work needed here, both in terms of developing ways of harnessing the possibilities of using Gen AI in this context, and also the evaluations themselves. Very quickly, the second example is taken from a living map and critical review we're currently developing for the UK Department of Health and Social Care on Gen AI applications in health and social care. And within this project, appropriately enough, we're again exploring the potential of using a Gen AI tool to help us select eligible studies. And this slide shows just a first few of 30 to 40 granular prompts from the latest of 4 iterations I've engineered using EPReview's new integrated GPT-4 auto-coding tool. Each of these prompts here produces a Boolean value in response, so either true or false, but we also have commands that can return strings or numbers. And when combined using the decision algorithm, these prompts achieved 82 to 85% agreement with human decisions, with recall of 0.95 to 0.98 and a precision of 0.86 to 0.87 on a stratified random sample of 100 records. So, in summary, most evidence synthesis still uses entirely manual processes, and machine learning is only used in very few of them, relatively speaking. There are many promising tools, but there are also barriers to implementation. That is, we don't always have the data to create good classifiers, or we don't have a good algorithm for knowing when we can stop screening, and so on. And the promise of Gen AI is only a promise at the moment, and we need lots of rigorous evaluations before we can see it fulfilled. So finally, very finally, to directly address the still open question of whether and to what extent these or any of the other AI tools I've covered today will ultimately enhance the outputs of evidence synthesis production, our key challenge is to ensure that we deploy these tools judiciously in ways that improve or at least maintain the quality and value of our outputs, and not in ways that only serve to increase the amount of low-quality reviews and maps being produced, which would at best mislead people and at worst kill them. Thank you.